All right, guys, welcome back. Let's get started. All right, so there are three topics that I will cover. One of them is the falling elevator. All right, so this was the main observation of the semester. Remember the guy on the 10th floor, the cable snaps. Elevator goes in a free fall, he's got a broken neck. Here's what most of you guys came up with, in essence. The guy's inside the elevator, an advanced storyboard. And so the person goes up, hits the ceiling. What goes up must come down. Either the first or the second impact is going to break his neck. The reality of it is the person remains on the floor at all times. The reason why the person never gets to leave the floor is because of free fall. All right, so something KLA came up with, right? Roughly about 400 years ago. Free fall is the motion under the influence of gravity and gravity only. In free fall, everything is going to fall at the same rate. So which means that the elevator and person inside will be falling at the same rate. But you're thinking, wait a minute, about the air friction? What about the air friction? What about the air friction? The person inside is shielded from the effects of air friction. The elevator is relatively heavy. It's a few thousand pounds. Distance falling is relatively short. So air friction, what kind of effect do you think that the air friction is going to have on the elevator? None, zero, nothing. So it's a practical free fall. So the person inside elevator, both of them are falling at the same rate. And guess what? There's a safety system. Safety system is going to bring the elevator to a stop gently. It's 2 Gs, 3 Gs, nothing more than that. Not large enough to do any harm. Yeah, you have a person inside with a broken neck. So the question is, how did that happen? Is this scenario even remotely possible? Well, regarding how the person broke his neck, I think it kind of depends on what you do inside a falling elevator. All right, so you find yourself in a falling elevator. What would you do? Imagine that you're about 3 steps away from the handlebar. You're caught in the middle somewhere, 3 steps away. All right, what would you do under the circumstances? Number one, you're going to be feeling weightless. And then you're going to think to yourself, number 2, panic. Oh my God, I'm going to die. If I could just balance myself, I kind of remember that you got a handlebar 3 steps in the backward direction. So why not walk? Can you walk inside a falling elevator? If you did, what do you think is going to happen? The other thing that I hear is jumping up from the floor. When do you jump? How do you jump? Can you even jump? What do you think that's going to make that much of a difference? The third one, lying down on the floor. This is high school physics teacher's favorite. Lie down on the floor. Why would you want to lie down? What's the purpose of it? Seriously. A lot of the high school physics teachers will say, oh, you have to lie down on the floor because it's going to disperse the impact force. True. You don't think your body can handle 2 Gs. How about 3 Gs? All right. Can you lie down even if you wanted to inside of falling elevator? How would that work out? The reality is you
have only experienced
and the elevator are falling at the same rate. So what that means is you will become suspended relative to your center of mass. Your center of balance is located here. This is your center of mass. You will become suspended relative to your center of mass, which means that the distance between your center of mass at the bottom of the elevator is going to be fixed. This distance, center of mass, and the floor is fixed. There's nothing you can do to close that gap unless you're pushing up against a floor or a ceiling or something. It's not going to happen. All right. So you will maintain that relative position. So notice that you can move relative to your center of mass. You can move sideways, just like the way he's doing it. And you can probably spin relative to your center of mass. If you could, though, it's going to be very slow. All right, so you need to pull your knees in and lean backward, and very slowly you can start rotating or gyrating. So those are 2 things that you could do. All right, now let's go over each and every single scenario. Can you walk inside a falling elevator? The answer to that question is no. Why not? Because walking requires friction, and friction requires that you're in contact with the floor. How much of a contact do you have when you're in a free fall with the floor? None, zilch, zero. No normal force, which means that there's no contact. Without contact, you cannot. Without being in contact with the floor, you cannot walk. Not going to happen. So what would happen if you were to move your legs as if you're walking? Your body is going to start to get out of alignment. Your body's going to do this. It's going to sway back and forth, back and forth. Well, at some point, your body's out of alignment or getting out of alignment. The safety system is going to kick in. And when it does, if your body's out of alignment, what do you think the worst that can happen? All right, how about jumping up from the floor? What do you have to do in order to jump up? You have to bang your knees in order to jump up. What happens when you bang your knees in this scenario? You end up losing contact, all contact with the floor. All right, so that's not going to work. The only thing that you could do maybe is to stretch your feet and then push up against the floor. Now what happens? Well, it's going to give you a small relative speed relative to the elevator, which means that you're going to float to the ceiling, hit the ceiling, bounce back, and come back down. That's it. That's how it's going to happen. Do you want to be floating up and down inside a falling elevator? while it's dark inside? Absolutely not. All right, so because your body is going to be all over the place, you don't want to hurt yourself by doing something like that. So walking is not going to work. Jumping is not going to work. How about lying down? Well, let's pretend that you can lie down for a second. Okay, I'm not entirely sure how you think you're going to be able to lie down without pushing up against it. Even if you could get your body parallel to the ground, which I don't see how you could do such a thing without pushing up against anything. Let's pretend that you can. All right, you're going to be getting your body parallel to the ground, roughly about 3-4 feet off the ground. All right, so that's not going to work. It's not the best option. If your body's slightly tilted, obviously you can break your neck or your feet, your legs. And then how do you even get your body parallel to the ground? So, all right, so lean back, pull your legs in. More than likely, it's going to give you a relative rotational speed. So you don't want to be rotating or spinning instead of falling out of it, because at some point you could be upside down. So those are 3 possible scenarios as to how you can break a bone instead of falling out of it. Even if you did everything the right way. So the best thing to do is do absolutely nothing. In the worst case scenario, you may end up wetting yourself like that, you can live with, right? So because there's going to be a safety system, when it kicks in, you will feel about 2-3 G's of acceleration. So that's the extent of it. The reality of it is you can still fall, lose your balance and fall and break your neck. It's possible. How? You're feeling weightless. You're not doing anything. You're feeling weightless. At some point, the safety system kicks in. And then the elevator starts to slow down, right? As the elevator is slowing down, you will feel 2-3 G's of acceleration. So which means that you're going to feel about 2 times or 3 times heavier. Just going from being weightless or feeling weightless to feeling about 2-3 times heavier, you may not be able to catch yourself. So things can still happen. All right, so something about gravity gives you a weight. All right, so the weight is the amount of gravitational force acting on it. Measured gravity or measure of gravity acting on a mass is known as the weight. If you wanted to lose weight, you would diet, right? That's one way of losing weight. Not the only way. You can also weigh yourself at the surface of the moon. You will weigh about 6 times less. On top of a very tall building, you're going to weigh slightly less. Here in Chicago, if you go up to the top of the Sears Tower, you're going to weigh slightly less. On an airplane, 30,000 feet up, about 2 pounds less. So something about gravity is still mysterious. In free fall, you know that everything falls at the same rate, regardless of their weights, right? So you got 2 objects, hammer and a feather, drop from the same height. They will both accelerate at the same rate and reach the ground at the same time. So that's what it means. So the question is why? Why is it that the weight of a falling object does not matter? Why is it that the mass of a falling object does not matter? Why is it that everything falls at the same rate? All right, in the back of your heads, you guys are thinking, oh, because everything experiences the same amount of gravitational pull. I'm thinking, nope. Unless 2 objects weigh the same, they don't experience the same amount of gravitational pull. The amount of gravitational pull that an object experiences depends on the mass. Well, massive objects will experience a larger gravitational pull, hence the reason why they're heavier, and lighter objects will experience a smaller gravitational pull, hence the reason why they're lighter. Yeah, everything falls at the same rate. Regardless of how big, how small, how heavy, how light, everything falls at the same rate. Gravity does not discriminate. So the question is, why not? Why is it that the weight of an object does not matter in terms of how fast it falls? Nature of gravity is a force, right? Gravity is a force. All right, so what is the nature of gravity? It's a force. Next question. What causes it? And whether or not the gravity extends all the way out to the moon. All right, so these are the questions that we actually looked at before. We know gravity is a force because gravity does exactly what a force does. So the force causes acceleration, so does gravity. So which means that the gravity is a force. So gravity causes objects to accelerate at a constant rate, implying that it's a constant force. So the force acting on an object is known as the weight of an object. All right, so F equals ma is the force. We know that the force originates from the center of the Earth because the falling objects do accelerate towards the center of the Earth. So the force is going to point in the same direction, obviously. So the next question is, does this force extend all the way out to the moon? Now that's a valid question. Well, number one, we know for a fact that there's a force acting on the moon, because if it didn't, the moon would have gone in a straight line at a constant speed. The moon, instead of going in a straight line, it's changing direction, right? So that implies that it's accelerating. And if it's accelerating, and there's a force acting on it. Now you can figure out the direction of the force by looking at the direction of the acceleration. So you know that the acceleration and the force are in the same direction. So which means that this force, whatever this may be, I'm not saying gravity is yet, must be originating from the Earth itself. All right. So the reason why I don't want to just jump to the conclusion that, hey, look, whatever the force that pulls the apple down is the same force that extends all the way out to the moon. I don't want to say that yet. Why not? Because listen, that apple falls, the moon doesn't seem to be. All right. So that's the reason why you go, oh, okay, let's just investigate a little bit more. So what do we know? The Applefrost moon does not appear to be. And on top of that, in modern days, we know, all right, we know that the astronauts in space appear weightless. Okay, guys, being weightless in space means that you're not experiencing gravity. All right, that's the way it's interpreted. Remember, weight is the measure of gravity. All right, so weight is the measure of the gravitational pull acting on a mass. All right, so if an astronaut is truly weightless in space, which means that this person is truly not experiencing a gravitational pull, then all of a sudden Newton's theory kind of does not make sense. All right, so if gravity extends all the way out to the moon, you cannot be weightless in space. All right, especially between here and the moon. You cannot be weightless between here and the moon. That's what Newton says. Newton says, hey, listen, for you to be weightless in space, you need to be in deep space, which means that you have to be literally light years away from the nearest planet, the star, whatever. All right, that's what it means. Light years. When I say light years, I mean, I don't know, like a billion light years, trillion light years. Reality of it is there's no place in space, if Newton is correct, there's absolutely no place in space where you can become weightless. That's what it means. All right, there's no such thing as being weightless in space. All right, so
lights, please.
So in order to answer these questions, Newton had to come up with the law of gravity.
Just dim the lights.
I'm on board. It's not electric. All right, so nature of gravity, it's a force. And then he discovered that this force is going to be directly proportional to the product of the masses. Product means multiplication. It's going to be inversely proportional to the square of the distances between the masses as measured relative to the center of mass. And times capital G. Capital G represents the strength of gravity. All right. So that's what he came up with. All right. Next question is, falling objects will accelerate at a constant rate. So the question is, why? All right, so this is the question. Why is it that everything falls at a constant rate? Newton came up with an ingenious answer for this one. It says the weight is caused by gravity, right? All right, so the weight is mg. Gravitational force is given by this formula. So which means that these two equations will be equal to each other. From here, you can isolate g. So the mass of the falling object is going to cancel out from both sides. So it's not going to matter. All right, so, and then r in this formula is going to represent the distance between the mass of the apple and the mass of the Earth. And you guys are thinking, oh, the distance is 0. I'm thinking, no, it's not. Remember, you measure the distances relative to the center of mass. All right, so which means that the r is going to be the distance between the center of the apple and the center of the Earth. Give and take, it's going to be the radius of the Earth itself, right? So that's what you're looking at. So here's the formula. And so this formula gives you an expression for g, tells you what it is in essence. So the best thing to do now, check to see if the formula is correct before we draw conclusions, all right? Because there are two predictions from the theory, from the formula. It says how fast the objects will fall will depend on the mass of the planet. It's going to depend on the size of the planet. So it's directly proportional to mass, inversely proportional to size. That's what it means. So let's check to see if the theory is correct first. Here's the measure value, observed value of the measure value for the acceleration due to gravity. Here, and the predicted value is going to come out of this one. All right, so when you plug the numbers in, the predicted value is also non-bounding. So the measure value and the predicted values match, right? If the values match, which means that this theory is correct. This formula correctly represents gravity. All right, so now we have a bit of an answer. We know that the objects fall at a constant rate because the mass of the object, falling object, is not going to matter. What's going to matter is the mass of the planet or the star or your fourth temple. It doesn't matter. That's the only thing that matters. And then the other thing that matters is the size of it, or a square of the size of it. So if you find a planet the same size, twice as massive, it's a 2G environment, which means that you will feel 2 times heavier. If you find a planet the same size, 5 times more massive, it's going to be a 5G environment. And then we have this inverse relationship here that we will have to focus on because this one is counterintuitive. So for a given mass, what if you find a planet which has got the same exact mass as the Earth does, except it's 2 times as small? All right, so if it's 2 times smaller, 2 squared is going to be 4, so which means that the acceleration due to gravity is going to be 4 times larger, so it's a 4G environment. If you find a planet which is 3 times as small for a given mass, so it's going to be a 9G environment, 4 times as small, 16G environment, and 5 times as small, it's going to be a 25G environment. So you end up getting some predictions out of the theory. All right, so how do you know that this theory is correct? Well, the only way you know your theory is correct, or his theory is correct, or anybody's theory is correct, to check it against reality. So the experimental and the theoretical numbers match. That's how you know. All right, so the next question is, does gravity extend all the way out to the moon? Well, we know that there's a force that extends all the way out to the moon. So the question is it gravity? All right, so the best thing to do is figure out what the acceleration due to gravity would be at that distance. All right, so it's got to be a very small acceleration. And then measure All right, so if this acceleration is due to gravity, Newton said, it would cause a measurable acceleration. So the acceleration of the moon would be about 0.00273 meters per second squared. So here's the theory, here's the prediction. All right, so how do you test this prediction? Measure it. You have someone measure. All right, except you got to remember, this guy lived 350 years ago. This is a very small acceleration that needs to be measured through a distance of 250,000 miles. All right, so forget it. All right, so no way to measure an acceleration through that distance. So it's not going to happen. All right. So instead, what they were able to measure instead of this acceleration was a deviation of the moon from a straight line. All right, so evidently they were able to measure the deviation of the moon from a straight line onto this trajectory that matches the curvature of the surface of the Earth. So what's happening is the moon is deviating from a straight line 1/20th of an inch per second towards the Earth. In essence, the moon is actually falling towards the Earth. This is the distance falling towards the Earth, 1/20th of an inch, 1/20th of an inch per second. So that's what the astronomers were able to gauge or measure at the time. So here's the predictive value. So is it possible to use the predictive value to then come up with a prediction regarding how much the moon is going to fall from a straight line and check to see if that prediction matches this observation? As it so happens, it was possible to come up with a formula, except Newton had to invent calculus in order to come up with this one. So this is the distance that the moon is going to fall towards the Earth at this acceleration within this time period. So this number goes into that formula. T is going to be 1 second. And then plug the numbers in. And once again, this formula is going to give you a number in terms of millimeter, which happens to be 20th of an inch, 1/20th of an inch. So here's the predicted deviation, 1/20th of an inch. Here's the observed prediction, which is 1/20th of an inch per second. So this is the proof that gravity extends all the way out to the moon. So the force that pulls the apple down and the force that extends all the way out to the moon
Most of us
are the same forces. Are the same forces.
have only experienced a tiny slice of time.
Except the problem is this: in space, astronauts appear weightless. Question: why? You guys are thinking, oh, so that's what NASA means when they say microgravity. So now you're okay with the idea that there's gravity in space, but you're thinking that it's just so incredibly weak. It's so incredibly weak that you don't experience it. All right, so your mind comes up with these weird answers, and it's normal because a lot of the times when the mind just comes up with these little explanations, these explanations go unchecked. And then all of a sudden you have this group thing thinking that all of you guys have the same answer, so it's got to be correct. That's not how things work, guys. If all of you guys have the same answer, that's called common sense. I mean, common sense is no substitute for education. It's more than likely it's 100% incorrect. All right, because your reality that your mind makes up is no substitute for education. Just get it into your heads. So you guys are thinking, oh, so it's microgravity in space, so you're feeling weightless because you're at least. Well, that's how does microgravity work? Let me just explain a few things for you. Imagine that the gravitational pull acting on you is microscopic, right? Does this mean that you're not falling? Does this mean that you're falling very slowly? What do you think that means? Let me tell you what should experience microgravity as far as you guys are concerned. If you're experiencing microgravity in the backs of your heads, you're thinking, oh, you're not going to be falling as fast. That's what it means, because translated to English, that means that if you're lighter, you're not going to fall as fast as a heavy object, which is not true. Which is not true. I mean, I weigh 150 pounds, and electron is the smallest thing that we get to play with normally whenever we're running on electricity through something. So we have this Zoom discussion, the recitation session that we're having. How much does an electron weigh, guys? Let's think of it in terms of its mass. All right, it's going to be 9.11 times 10 to the minus 31 kilograms, which means that it's got 30 zeros before you hit the first number. All right, that electron in a vacuum still falls at the same rate as I do. All right, that thing is almost weightless, for God's sake, compared to my weight. Yet we fall at the same rate because both of us got mass. All right, so you're in space and you're thinking microgravity because that's the term that the NASA uses, and that astronaut that you saw is almost 180 miles from the surface of the Earth. Let's check to see if it's microgravity. Microgravity means that the acceleration due to gravity is going to be 10 to the minus 6 something meters per second squared. That's what it means. Let's check to see if that's the case. So the space shuttle, 180 miles from the surface of the Earth. And here's the formula. Radius of the Earth plus the distance to the space shuttle. If NASA is right, it's going to be microgravity, which means that it's going to be 10 times, it's going to be 10 to the negative 6 something meters per second squared. You put the numbers in and you get a number which is almost 9. This is no microgravity. This number is slightly less than the gravitational pull that you experience at the surface of the moon, on the surface of the Earth, not the moon. So what that means is that person who weighs roughly about 220 pounds here on Earth is going to still weigh about 200 pounds in space. All right, so being in space, you end up losing about 15 to 20 pounds. That's it. Yeah, these people up here weightless. How's that possible? They're not weightless, but they will appear weightless. So the question is why? The answer once again came from Newton. He explained it in his book Principia. All right, so this is an analogy based on what Newton came up with. Imagine that you're on the moon's surface, the rifle that can actually fire bullets at varying speeds. Imagine that you can fire 3 bullets at the same time. And this is moving the fastest, this is moving the slowest, and all of them still reach the ground at the same time, right? Why? It's free fall. Projectile motion is a special case of free fall. In free fall, everything falls at the same rate. Everything falls at the same rate. Regardless of their horizontal motion, everything still falls at the same rate, so that becomes projectile motion. So you got this magic gun, and then you keep firing bullets, and the bullets, every time you fire a bullet, it moves travel than the bullet before, and then it travels faster than the bullet before. So notice that at some point, as the speed of the bullet increases, the trajectory of the bullet starts to match the temperature of the surface of the moon. At some point, it's going to match it perfectly. So what happened? Now, what happened is this bullet in orbit around the moon at a given speed. So when the projectile motion, the trajectory of the projectile motion matches the curvature of the moon, the planet, the star, or whatnot, all right, that's known as orbital motion. So which means that unless she takes a step sideways, she's going to take the bullet to the back of her head. All right, so this bullet is in free fall in the form of projectile motion around the moon. The same thing happens to the astronauts. All right, so free fall, person inside the elevator is going to feel weightless, boom, just like the person inside the space shuttle or the space lab that you're looking at. And this person is also in free fall in the form of projectile motion. In free fall, you will appear weightless because you and your environment are falling at the same rate, just like the person inside the elevator and the elevator are falling at the same rate. So which means that the person won't be in contact with the floor under any circumstances, and the person will become suspended relative to his or her center of mass. So Newton's obsession is, if an apple falls because of gravity, why doesn't the moon also fall from the sky? At least that question, the mystery is resolved. Apple falls because of gravity, so does the moon. Except the moon falls in the form of projectile motion, whose trajectory matches the curvature of the Earth, and it falls from a straight line onto that trajectory a distance of 1/20th of an inch per second. That's it. All right, so the application is levitation. Is human levitation possible, if that's the case? Can you overcome gravity, mind over matter? All right, so levitation is a weird thing because it borders with a lot of people's religious beliefs. A lot of you guys, deep down, you know that's probably not possible, but you like to believe that it is. And you like to believe that there are people who could actually do something like this, like Jesus walking on water, for example. So in every single religion, regardless of what your religious beliefs are, people believe they're comfortable with the idea that if you are godly enough, if you are saintly enough, it wouldn't surprise you that you could somehow levitate along the way. All right, so there's a lot of anecdotal, I don't want to say evidence, but there are stories. Just go to Wikipedia, and every single religion, you will find people, according to some, who could levitate. So the question becomes, can you overcome gravity, mind over matter? Is it possible? All right, so this was a major mind twister, so I decided to put the emphasis on capital G. The reason why I decided to put the emphasis on capital G, because capital G is the strength of gravity. And it's a small number, it's a very small number, which means that you got 10 zeros before you hit the first number. So can you overcome something that's small? And then I made a comparison between this number and a penny in your pocket expressed in terms of $1. Notice that the magnitude of this number is going to be much smaller than a penny in your pocket. And in order to solidify this analogy, I said, hey, so what do you have in your pocket if you got less than a penny? And you know you got nothing in your pocket under the circumstances. So in essence, you're looking at a number which is less than a penny in your pocket, right? So this number is something but which is almost nothing. So can you overcome something like this, mind over matter? And most of you guys probably think that you can't because you've never tried it. Okay, just because you cannot do something does not mean that it cannot be done. I'm pretty sure you guys wouldn't know how to build it. The cell phone, you wouldn't know how to build a car, you wouldn't know how to build an airplane, but we do it all the time. So just because you cannot do it does not mean that it cannot be done. All right. So that's what it means. And there are people who think that they can overcome something like this, mind over matter. So the question is, can you really? All right. So that's what we're going to be focusing on. And all of a sudden, and then I showed you every single thing that considered levitation. And then at the end, you notice that it's every one of them is an illusion or magic trick. And then a bit of a discussion about Tintin. All right, so the The artist is also the author, and Tintin is a Belgian journalist. This is a comic book from 1950s, and then the artist was actually basing these adventures, Tintin's adventures, loosely upon his own life experiences. So Tintin is in Tibet and then runs into this monk, and then the monk starts levitating. And then next thing you know, this time you're looking at a Nepali monk doing the same thing. All right, and there's no levitation stick, nothing is touching the ground, with the exception of this thing, obviously. And that thing is actually dangling. I'm not sure if it's touching the ground. You don't see any feet. And the guy there's a cameraman, and then obviously there's a stage magician right next to the cameraman. So they're looking for all these wires and cables or whatever, and there's nothing that they could see. So the question is that true levitation?
For that, I think there was something that he didn't want me to see.
Would that be real levitation? So the answer to that question is they almost created the illusion that this could be a real levitation, because this guy not a magician. He's not asking for money. He's not putting on a show for 1,000 people or whatever. So he had to be convinced to do that. And you can make all those kind of arguments if you're a believer of levitation. But realistically, though, real levitation wouldn't look like that. Why not? Because the Earth is spinning on its axis, right? About 1,000 miles per hour. If you could just cancel out gravity, what would happen? You would keep moving in a straight line at a constant speed at 1,000 miles per hour. So relative to this room, you would start to rise up towards the ceiling gradually. That's what would happen. Okay, you can't just go up and put the brakes on and stay there and then come back down. That's not how real levitation will look like. All right, so that's one answer. Is this true levitation? No. I don't know what he did. Looks real impressive, but I've seen it done better or same quality by some street musicians, and I don't even, or state musicians. I don't know how they do it either. So either way, I don't care. Neither is real levitation. And let's imagine that this is the strength of gravity. Can you overcome a strength of gravity just like that? Mind over matter. Okay, guys, think of it this way. This is not the only thing you're overcoming. All right, so you got to take this and multiply by the mass of the Earth and divide it by the square of the size of the Earth. It's going to give you a number which is roughly about 10. And then you need to take this number, multiply it by your mass. At that point, I got my 150 pound weight. Can you overcome 150 pounds, mind over matter? How does that go? The answer to that question all of a sudden becomes no. And there's a reason for it, because the internal forces would not cause acceleration. You cannot grab your nose or the other arm and lift yourself up off the ground. It simply does not work out that way. All right, only an external force can cause you to accelerate. So this spiritual uplift, or in my dad's vernacular, the holy force has to be an internal force, if there's such a thing. And internal forces will not cause you to accelerate. It's not going to happen. All right, it will not happen. If I were to see someone and start levitating in the fashion that I described it, if this person gradually would start rising towards the ceiling, I would go, okay, yeah, I can see that to be a levitation. All right, and then I would go, oh, so the spiritual uplift is not an internal force; it's an external force. That's the only connection that I would make. All right, and that's the extent of it. And I would go, okay, well, so there's such a thing, and there's no evidence for it, obviously. So, all right, so circular motion. All right, so in terms of the circular motion, this video is not going to play.
Off the bridge while tethered to the cable.
Stand up. All right, so when these guys did their pendulum move at the bottom of the arc, it looked like the cable snapped. So the question is, did it? And if the cable snapped, a lot of you guys thought that, oh, they didn't pick the right cable. So which means the cable didn't have the proper column. There's a bunch of daredevils. They were going to do this regardless, and they thought that they were taking a calculated risk. As this all happens, the calculation must have been wrong. All right, so that's the way I thought initially. And then looking at the numbers that they were giving, I done the calculations, only to discover that they were fine. They weren't taking a calculated risk. Their computations were done correctly, and something else went wrong. All right, so doing the loop.
Number to drive through the loop, otherwise it's not going to be possible. So I had to concentrate.
So what is the magic number that he's talking about that you come up with? But I think I'm not going to put the emphasis on that. Let's just put the emphasis on the terminology at this point, because you guys are taking conceptual physics. All right, so v squared divided by r is known as the centripetal acceleration. So that's the acceleration directed towards the center, multiplied by the mass is going to give you the centripetal force. Centripetal force is any force that's directed towards the center of a circle. That's what it means. All right, so it's centripetal is just a direction, right? Along the x direction, y direction, z direction, or along the r direction, the radial direction, is known as any force directed towards the center of a circle is known as the centripetal force. You're inside a rotor, the centrifuge suspended on a wall. So what's the centripetal force in this case? So the centripetal force is the force that's directed towards the center. So what is the force that prevents you from going in a straight line at a constant speed? What prevents you from going in a straight line at constant speed is the wall itself, right? So there's a surface force involved. So you're pressed up against the surface of the wall. The wall is going to apply the same force back on you, directed towards the center. So that force is the normal force, right? The surface force. Satellite orbiting the Earth, the force which is directed towards the center is going to be gravity. Car negotiating a curve, the force which is directed towards the center is going to be the static frictional force. So those are the examples of centripetal forces that you're looking at. So force is what causes acceleration. So this is the centripetal acceleration. All right, here's the centripetal acceleration formula. So inside a centrifuge, the centripetal force is the normal force. Satellite orbiting the Earth, centripetal force is gravity. Car negotiating a curve, the centripetal force is the static frictional force. All right, so we've already had a discussion regarding that. So all right, so the couple of things that we will discuss, the weight or the mass of the car is not going to matter in terms of how fast you can negotiate a curve. Mass gets canceled out of the equation. How fast you can negotiate a curve depends on the static frictional force. At the maximum speed at which you can negotiate a curve, the static frictional force is going to be maximized, and static frictional force only depends on the mass. So vehicle which is twice as heavy is going to experience a frictional force twice as big. Vehicle which is 10 times as heavy is going to experience a frictional force which is going to be 10 times as big, right? All right, so the mass of the vehicle is not going to matter regarding that. All right, so this is force summation that you're looking at. The inner force directed towards the center is going to be positive, away from the center is going to be negative in terms of centripetal forces. And it's directed towards the center, positive, W away from the center, so it's going to be negative. W and N are directed towards the center, so they're going to be positive. All right, so the only case that we will look at is going to be the pendulum move. All right, so speaking of the pendulum move, and then the only thing that we will be interested in is the conclusion of this one. So at the bottom of the arc, they said that they were going at 80 miles per hour. The cable was 200 feet. You got 5 people, their approximate weight is going to be 900 pounds. So what's the tension? They found a cable that can handle up to 4,000 pounds. So what is the tension that they induced on the cable? All right, so these are the conversions to the metric units for the computation purposes. So sum of the centripetal force, T is towards the center, that's the tension, W is away from the center, that's the weight, positive minus W. Here's the centripetal force formula, solve for T, so get rid of W from both sides. All right, so this is the only formula that we'll focus on for conceptual reasons. So faster you go, the larger the tension is, slower you go, the smaller the tension is. All right, so you plug the numbers and then do the conversions. Eventually, you come up with a number which is going to be 2,800 pounds. So that's the amount of tension that these people were inducing on the cable, 2,800 pounds. And they picked the cable that can handle up to 4,000 pounds. All right, so which means that they done their homework. This cable was supposed to handle up to this, more than this, obviously. So it wasn't the cable that's not. It was the connector. Can handle up to 2,700 pounds. All right, so let's focus on this formula. That's the only thing that you will need to know for the task. So in a pendulum move, the tension depends on the weight and plus the motion. All right, so the speed is going to matter, right? So faster you go, the larger the tension is. Slower you go, the slower the tension is. If it's not moving, the tension is only going to depend on the weight. That's it. All right, so a couple of more things and we're done. All right, so the weight of the vehicle is not going to matter in terms of how fast you can negotiate a curve because static frictional force depends on the weight. All right, so heavier something is, the larger the frictional force is. So which means that the maximum speed at which you can negotiate a curve does not depend on the weight. It's not going to change. All right, so you got a Ferris wheel sitting on a bathroom scale. At the highest point of the scale, it's going to be 0. All right, so at the highest point, if it's not moving, then it's going to have 2 forces acting on it. One is directed towards the center, that's the weight. The other one is going to be directed away from the center, so that's the normal force. But if it's moving so fast that you're feeling weightless, at that point, the normal force is going to be 0. So the only force which is directed towards the center would be the weight. So it would be 500 newtons. All right, so the next one is what happens to tension in a pendulum move at the bottom of the arc? Does it increase, decrease, or stay the same? Well, the tension is going to be sensitive to motion, right? At the bottom of the arc. So here's the tension, here's the weight, here's the speed. Faster you go, the larger the tension is. Slower you go, the smaller the tension is. All right, so that's pretty much it.